Hello and welcome to my presentation. First of all, I want to thank you, the organizers, for inviting me to give this presentation. I apologize also that I was not able to join this conference in person, but I hope that very soon we will see each other and have opportunity to collaborate. So the presentation that I want to give today is about European supercritical water-cooled small modular reactor. I'm from Karlsruhe Institute of Technology, and this work is performed within a joint European-Canadian-Chinese development on small modular supercritical water reactor. This was European part was financed, of course, by European Commission. It project ended around 2 months ago, and the base of the project was to provide the pre-conceptual design and the safety demonstration for such small modular reactors, where Europe was developing its own design, Canada the other one, and China the third one. So, and the idea was to compare and to evaluate these designs. The differences were significant. The European design was an interesting horizontal core, which I wanted to present today, where the focus was on the passive safety. Canadian was a heavy water one with a single pass, and Chinese had a two-pass flow, where the Canadian and Chinese, they both have a vertical core setup. So in general, supercritical water reactor technology is one of the six Gen 4 reactor types, where it is the evolution from the high-performance light water reactor, or it can be seen as the evolution, which itself is the evolution of the PWR. The most important thing is that it operates on above the critical point, so that's about 22 megapascal and 374 degrees centigrade for water. It has a single phase coolant, sorry, and it's a direct cycle. So there are no steam generators, and doing so, simplified design can be achieved, and the thermal efficiency will be also increased. So the base for this entire research, what Europe is considering, is established in 2023. This means that our project already started, but there is now established partnership on small modular reactors, where the scenario is set it up to 2050, where the idea was to get at least 15 gigawatt electric from the small modular reactors in order to replace the coal-fired power plants, to provide some district heating in the Northern European communities, to provide an industrial stream, and provide also hydrogen production and grid stability as well. For the European design, the strategy was set in, as I said previously, focused on the passive system. So lessons learned from the HPLWR showed that the siphon breakthrough during the LOCA was the key problem for the large scale. So HPLWR was a large scale 1 gigawatt supercritical design, where two passes were included, and still this effect of the siphon was not to be resolved. So here we were following the different strategy. So the strategy was to set a horizontal core and then to increase the number of heat-up stages to 7. We will see that this provides a lot of advantages. We can provide the passive decay heat removal for more than 72 hours. There is no need for high pressure injection, and the natural circulation established very fast. So the main design parameters are here. It's a 290 megawatt thermal at 25 megapascal to reach the efficiency of around 44%, and where the outlet temperature was 500 degrees centigrade. The mass flow rate was varying, so it's around 150 at the very end for the inflow. And you see we have 7 stages horizontally, which we will see immediately. So the key idea was to establish the steel structure to enforce the coolant to move as on the staircase. So comes here from the side, turns around and go into the core from the side, where the moderator water is in the separate channels, and there is a thermal insulation between these stages, similar to this. Now, when we look at the vertical cut, you see that this flow structure is quite complex. So feed water comes here in, control is through the orifice. So amount of water goes up to the upper plenum, the most of that goes down to the lower plenum, and then starts to circulate, entering from below and then passing the core. On the first look, it looks very complex, but it is described in detail in the paper, so it will be easier to follow. The key idea is just to enforce this natural circulation and increase the mixing by introducing additional orifices to control the mixing between the range here and the upper plenum itself. So we see what was the design idea was to, in the first 3 stages, so you see here is from 1 to 7, these are the stages that we're talking about. So from here, and there were 40 fuel assemblies in the first 3, then increasing to 60, and then increasing to 80 in the last 2 stages. So when we carefully provide this design, it appears that we can have a uniform pressure drop throughout the core, even though there was a 3.5 density change in the system because of 200 degrees centigrade temperature difference, and the supercritical water reacts by passing the pseudocritical point extremely, so that the density has very strong changes. However, the controlled uniform pressure drop was one of the key questions that have to be resolved. So, describing the fuel assembly, essentially the assembly is the same as in the HPLWR. It was investigated in detail. The development of high-performance light water reactor was over 2 European projects, including then fuel qualifications that, so overall like 20 years of advancement. 12 years of advancement. And what we see is that cladding is considered to be 310 stainless steel, and as alternative 800H was also investigated. It appears that 800H is more promising, and the assembly box has this sandwich structure where the liner is zircaloy and zirconia is the insulation. So cladding, as I said, 800H to 310S, standard material for the pressure vessel, and the question was actually to be addressed to the challenges for the material side. So the corrosion in this high pressure, high temperature environment is one of the key questions. And then the project started with irradiation experiments, but they are very expensive, so they are up to now partially finished. And that was the Canadian part. The partners from Canada were doing that, so that finally the question of the stress corrosion cracking remained one of the, or as expected, was one of the key points in the evaluation. So what was the principle? As I said, we required to have increased passive safety by providing the isolation condenser system, the ADS, and one of the important points was this thermal inertia by the subcooled water, because we had 100 cubic meter of water in the system at the lower temperatures, so that this can be efficiently used. The important point is that high pressure injection should not be required. So the system have to be sufficient for decay heat removal by natural circulation. Now, how the safety system sketch looks like. So we have here in blue is the normal operation range, then in the red is the active safety system, and the green one here is the passive one. So the primary system include the isolation condensers and the valves and the accumulators as well. We evaluated this setup in a different way here just to make you an impression. This is a result of the coupled code between Apros and Monte Carlo Serpent code, where this modeling was changed. The core inflow was variated slightly to see the effects on the outlet temperature and how the temperature distribution in the coolant and the moderator was distributed. We have afterwards also the accident analysis, which is performed. Actually, in this ECC Smart, we had a dedicated work package to the thermal hydraulics and safety, then one to the reactor physics and one to the material side. And this is how they are interacting. I was leading this work package for the thermal hydraulics and safety. So here, from the system codes, RELAP and APROS were used, but we also used sub-channel codes like STAFAS and ACERT, and numerous CFD investigations have been done. However, we don't have time, so I just wanted to show you the relevant system analysis. So the key point is that by the large break loca, temperature was at 780, and both codes were able to show the similar result. And on the long-term station blackout, the peak cladding temperature was 680, so this was all within the design expectations. So material expected the maximum temperature not to go above 850, and this was definitely reached. So interesting is also that in the long-term station blackout, the distribution was that the equilibrium was on the 200 degrees achieved, and there was no operator action required for the first 72 hours, so that the natural circulation established actually quite fast and have stable passive cooling. For the large break loca, the initial was 200% on the cold lag, then the double-ended guillotine, and no ECCS for the first 20 seconds. So we see that the peak cladding temperature was 780, and as I said, 850 was material limits. So interesting was to observe what is going on with the subcooled buffer due to the thermal inertia of this 100 cubic meter water at the lower temperature. as we provided a lot of this evaluation, I wanted to show you now some very, very short summary on how the setup between the design was. So European was 290, thermal Canadian was nearly the same. Chinese one was 50% higher, and the outlet temperature for the Canadian one was considerably higher than for the European and Chinese version. And you see that we have 7 flow passes in the horizontal structure, where these two vertical were slightly different. So the evaluation of the peak cladding temperature in local for Canadian one was fairly high, but it appears that this could be a problem also due to the heat transfer correlations, so that the standard heat transfer correlations provided interestingly huge differences in the evaluation. So it opened a number of questions induced from there how to operate the system code. And we will see this is one of the key points for the future of the supercritical water designs. Here I wanted to show you how the supercritical SMR compares to the other technologies. So this integral PWR like NuScale, we see this is similar power ranges of all of them as expected. However, we have efficiencies on the molten salt and the supercritical considerably higher. However, refueling is also similar. So all of them are basically competitive currently, but all of them are still far away from real applications. Even NuScale, which was announced to be ready, but had problems. What are the challenges that remain? As I said, the irradiation was not completed, so these questions are still open. The stress corrosion cracking is one of the key issues for all new materials, particularly in this case where we have high pressure. Our investigations showed that 800H remained quite stable, so that the corrosion layer thickness do not increase too much. It changes the structure, but the thickness remains, so that the heat transfer due to the conductivity was not strongly differ, and the roughness of the surface induced positively, of course, the turbulence generation, so that we could go on to the heat transfer deterioration, which is a very specific problem for the supercritical fluids. However, they are connected to the turbulence generation, and from there, the corroded surface, the rough surface, is supportive, so that we don't have this sudden reduction. Even the coolant is passing through this pseudocritical point, because it goes from 280 to 500 degrees centigrade, where the water was have a pseudocritical point at 370 approximately. So, and as I said, now one of the main points is the regulatory framework. So we have the codes are still not validated, so they are in development, all of them, RELAP 5 or APROS. So the database, the tables for the material fluid properties are included, and the codes are converging, can calculate properly. However, the validation is still not sufficient. And even though there was a project on a fuel qualification test, this is still an important question which have to be further investigated. So the roadmap was actually the pre-conceptual design, which is provided within the ECC Smart project that was between 2020 and April 2025. So the next step would be to improve the knowledge on the flow and corrosion together. There is a facility in Czech Republic that can be used for this. However, these experiments are very expensive, and the question is now, can we establish this investment within some project? In addition, of course, the design should be further developed, and the prototyping of components should be started. The coupling of the code is still to be further developed as well. So the near term would be in this direction. The key achievements were that we have demonstrated very efficient passive safety. The natural circulation starts within 200 seconds and remains for long time. So leading to the excellent accident performance, so that the peak fighting temperature do not go over 780 degrees in the worst cases, and the subcooled buffer provides a crucial grace time, so that we have now the possibility to have efficient safety systems where 40% of thermal efficiency could be achieved. And this design was intensively evaluated with various kinds of codes with the system and sub-channel and different CFD calculations, DNS, LES, runs. So coupled codes with Monte Carlo and independent development on the reactor physics side. And also what was important is it was building on the knowledge. Number of people were included in the HPLWR project previously, me as well. So to conclude, we could demonstrate that the supercritical water small modular reactor is feasible. It has a superior enhancing of the passive safety due to this horizontal core design. However, this horizontal core design is exotic, I would say. Even there is a CANDU, but CANDU is heavy water is quite different. What is the current situation? The entire industry is established. So there are supercritical water fossil power plants, which are major technology. They are implemented in many countries. So here in Karlsruhe, we have one. However, the nuclear reactors on the supercritical water are now becoming a low priority politically, and this is in many countries the case, so that the R&D investment that is required is now questionable. So we'll see what the future brings in this direction. So I would like to thank you very much, and I would be very happy to answer your questions. Just send me an email, and thank you again, and see you soon. Thank you. Bye.